Chapter 11, Intermolecular Forces. Intermolecular forces are forces that occur in between, or like an interstate, go between states, or like an internet, go between computers. And these intermolecular forces happen between molecules. Between molecules. Now, since the word is inter, we know that it's between molecules, not the thing inside of molecules. And since it's molecular, we know that molecular substances are nonmetals only. Only nonmetals that are stuck together. So look for things that have only nonmetals, and then they have forces in between for intermolecular forces that we're going to talk about in this chapter. Most of the time when we talk about intermolecular forces, we want to talk about changes of state. Changes of state from solid to liquid to gas. And so watch for those throughout this chapter. Intermolecular forces are many times also confused with ionic bonds. Ionic bonds, remember, happen between metals and nonmetals, or metals and polyatomic ions, or two polyatomic ions. Remember, these are not intermolecular forces, these are ion forces, where ions electrostatically attract to other ions. So keep those separate, because we'll talk about changes of phase of these things, but remember, when those change phase, we're actually changing this attraction right here, which is lots stronger than the intermolecular forces we're going to talk about that work between molecules. It's also confused with atom-only attractions that occur. Atom-only attractions that occur would be things like that occur between two copper atoms. Remember, these are called metal-to-metal bonds or metallic bonds. Metallic bonds, of course, occur just between two metals, and we'll talk about the phase change of those things, but remember, we're talking about the change in this attraction that's happening between the copper atoms themselves. Another one would be between just two atoms. So inter-atom attraction, like between two argons. These are similar to intermolecular forces, similar to the intermolecular forces that we're talking about, in that they're nonmetals only. They're nonmetals only, the argon and argon. But, keep that straight, that that's actually just an atom-to-atom attraction. So, once you've written these notes down, pause if you need to now to back up to get these notes that are handwritten. Once you have these down, make sure that you have your notes out in front of you, that include the electronegativity review, and then it goes on to dipole moment, and then how things stick together. So this is section 11.1 in the textbook, and before we go on with section 11.1 and some sample problems there, we need to review just a few things. That play an important role in intermolecular forces. The first one is, since we're talking about molecules, remember things that are nonmetals, we have to talk about electronegativity, because then we'll have to talk about dipoles that form in there, because those are very important to make molecules stick to molecules. Okay, so electronegativity, remember, on the periodic table, fluorine is your most electronegative element, and it increases up and to the right. And the most electronegative thing, remember, is in the upper right-hand corner, the element fluorine. And then the least electronegative, of course, is the one way down in the lower left-hand corner, things like rubidium, cesium, barium, things like that. And so electronegativity increases up and to the right. And the three most electronegative elements in order are fluorine, oxygen, and nitrogen. And remember, that's because they have small atomic radii and have a very exothermic electron affinity, and they want to get this noble gas configuration till they'll end up looking like neon. Now, chlorine's also quite electronegative, bromine not so much, sulfur as well, but these guys up here are the prime movers, the ones that we're going to be talking about a lot when we talk about intermolecular forces. So keep that trend in mind as we talk about these forces. Secondly, we need to talk about dipole moment. What the heck is a dipole moment again? Remember, if we have a molecule such as H F. This attraction for electrons is towards the fluorine, the most electronegative element. And we can say that there's a partial negative charge over here by the fluorine and a partial positive charge over here by the hydrogen in this molecule, making this be what's called a polar molecule. A polar molecule because it has two poles, and that's where the word dipole comes from. Di meaning two, pole meaning positive and negative. And they just put this fancy word moment at the end of it too to mean that, hey, it has a dipole at a particular moment where this is positive and this is negative throughout the molecule. So these two ideas, electronegativity and dipole moment, are really huge in understanding how molecules stick together in these intermolecular forces. So let's talk about the four types of intermolecular forces and how these make things stick together. We'll start with the most basic kind that are called LDFs, or London dispersion forces. London dispersion forces. London dispersion forces occur between everything that is molecular. It even occurs between just two nonmetal atoms, like, for instance, that neon to neon attraction that holds neon atoms together. Even those are affected by these London dispersion forces, even though these aren't molecules. Okay? They occur between everything. And what they are is what's called a momentary polarization. A momentary polarization. And so if we have a molecule like, say, for example, CH4, at one moment or instant in time, the electrons that are shared between carbon and hydrogen right here, I'll just illustrate them as little e's, are both right around this hydrogen. At that same instant, maybe the electrons that are shared between the carbon and the hydrogen are right here, and between this one are right here. And so we have 6 different electrons that are kind of built up on this side of the molecule, giving it a momentary negative charge over here. Which means since the electrons kind of left and at that moment went to this side, we now have a momentary positive charge on this side. This instantaneous dipole allows this molecule to attract to another molecule that probably has the same thing going on. So there's another CH4 molecule that's right next to it, and at that same time, maybe it's having the same kind of instantaneous polarization where there's a negative here and a positive here, and this negative attracts to this positive, causing them to stick together. This instantaneous dipoling that occurs is called a London dispersion force. And of course, the more electrons a molecule has, the more London dispersion forces something could have. The more LDF something could have. So the greater the number of electrons, therefore the greater the LDFs that something possibly has. Okay, that's number one. It occurs between everything. Second type are dipole-dipole forces. On your notes sheet, it's listed as DD, and I'm running out of room, so I'm just going to write it right down here. Dipole-dipole forces occur only between polar molecules. Whoops, can't spell molecules. Only between polar molecules. And polar molecules, remember, are ones that have a dipole moment, like, for instance, HBr and HBr. Now, these are both, one of them is they both are polar molecules in that bromine is more electronegative than hydrogen, and therefore it pulls the electron closer to itself, and the hydrogen is left with its nucleus a little bit more exposed, giving it more of a positive charge. Right here, a little more of a positive charge here. Right here, a little more negative charge. Remember, this isn't instantaneous. This occurs all the time because bromine is a little more electronegative than hydrogen. This negative and this positive then attract to one another. And this attraction, this dipole-dipole attraction, is fairly strong. Now, there are still London dispersion forces going on there. There are still some London dispersion forces going on in there because it occurs between everything. But there are also this dipole moment attraction right here. This dipole moment attraction right here that's going on inside or in between these two molecules and all the molecules that are around it that are HBr or similarly polarized like this. So that's a dipole-dipole force. The last one, I'm sorry, the third, there's actually one more after this, is called hydrogen bonding. And this says H bonding on your sheet. I ran out of a little room, so I'm going to write it right down here. Hydrogen bonding is a special type of dipole-dipole force. Special type of dipole-dipole force. And it only occurs in molecules that have a hydrogen connected to an F, an O, or an N. It has to be connected to phone. So H has to be connected to an F, an O, or an N. Otherwise, you can't have hydrogen bonding. So what's an example of this? Well, let's say, for example, that you have a molecule like HF. In this case, it's polar, just like HBr was, in that the electron is pulled really close to fluorine, and hydrogen is left with its nucleus very exposed, and it has a very positive charge. And then it sees another HF, or another hydrogen bonded, another substance that could undergo hydrogen bonding. And these two things, this negative and this positive, attract, just like is in a dipole-dipole. The only difference is that this is super strong in comparison just to the regular dipole-dipole force. So if you have two molecules and one of them has hydrogen bonding, whereas the other one simply has a dipole-dipole force, this one sticks together way better, and therefore its melting point and its boiling point and all phase change things that are associated with it would be much more influenced by the hydrogen bonding. So watch for that. Watch for the NOF. It spells NOF backwards, or else it spells phone forwards, whichever way you like to remember it. NO and F, or FO and N. And remember, when it's connected to a hydrogen, you've got hydrogen bonding. That's the third type of intermolecular force. And then the last one is kind of intermolecular, kind of not. It kind of borders on that area where it's ionic bonding, and yet it's also an intermolecular force, and it's called an ion dipole force. This is when you have an ion, like for instance sodium or something like that, and it's attracted to something that has a dipole moment, like for instance water molecules. Water molecules, of course, are very polar in that the electrons are attracted towards the oxygen fairly strongly, making it a pretty good polarized molecule with a pretty strong negative charge here and a pretty good exposed nuclei of the hydrogen atoms right here, giving it a positive charge on that end. And the positive of the ion would be attracted to the negative of the dipole moment of the other molecule. This attraction is pretty darn good. And it happens, of course, when things dissolve in water. It also occurs when other ions would dissolve or be attracted to things that have dipoles as well. Interestingly enough, water itself sticks together really well, because what kind of force is it that holds water molecules to other water molecules right here? You might say, oh, it's a dipole-dipole force, and you'd be correct, but it's actually a special kind of dipole-dipole force because hydrogen is attached to an F, an O, or an N. And you go, oh, yeah, that's called hydrogen bonding. Yes, water intermolecular forces with itself in hydrogen bonding, which causes it to stick together quite well. Well, that's the first page of the notes. Let's go on to the second one, where it starts with, so what sticks together the best? So what sticks together the best? And the answer to that is really, it depends. And I know you don't like that answer, but that's okay. You can get over it real quick. But it depends on a couple of factors. Number one, Remember I said that everything's got London dispersion forces. And if something's a really, really big molecule with lots of electrons, this might be the absolute driving thing that holds the molecule to another molecule. The second thing, and probably the stronger thing than LDFs, are the dipole-dipole forces, and for sure the special case of hydrogen bonds. Hydrogen bonds are 10 times as strong, probably, as something like just a straight old dipole-dipole force. And these overshadow LDFs by far if the molecule is of similar size. So let's look at some sample exercises and let's see how these intermolecular forces can help us identify things that change phase and when they're going to change phase and, well, maybe even if they're going to change phase. If you want to follow along with these in your textbook, in the 10th edition, they're on page 449. Of course, if you got a different edition, they're going to be on a different page. But this is sample exercise 11.1, and it says the dipole moments of acetonitrile and methyl iodide are 3.9 and 1.62 respectively. Remember, there's a way you can actually calculate the dipole, and we didn't do a whole lot of that, but it's just a rating scale that tells you what the dipole moment of them are, and the bigger the number, the more dipole moment they have. Which of these substances will have the greatest dipole-dipole attraction among the molecules? And of course, the CH3CN has a dipole moment of about 3.9, and then the CH3I has a dipole moment of about 1.6. So, of course, the one that will have the greater dipole-dipole attraction is the one with the bigger dipole moment, because that will attract better to another CH3CN. The more polar the molecule, the more ability it has to stick together with other molecules of like polarity. Okay. Now, of course, both of these types of molecules right here, when they stick together with each other, hold together also by London dispersion forces, but it doesn't ask about that. It just says which substance would have the greatest dipole attractions. Okay. Letter B. Which of these substances will have the greater London dispersion attractions? Now, London dispersion attractions, remember, depend on the number of electrons in the molecule, the number of electrons in the molecule. And this is generally associated or directly proportional to the molecular weight of the substance or molecular mass of the substance. So you've got to look at both of these, add them up on the periodic table and say which one's fatter or which one's bigger. And if you add this up, this is 12, hydrogen's 1, so there's 3 of them, plus another 12, plus another 14 for nitrogen. So just approximating this, we've got about 27, 37, 47, maybe about 50 for a molecular weight. Maybe, that's generous. Okay, and then this one right here, we got carbon at 12, hydrogen about 3, and the iodine, if you look on the periodic table, iodine has an atomic mass of around 127. 127, that's 130, 140, 145 maybe just being, a little bit generous. But anyway, obviously, iodine's got a way bigger molecular weight. And if you just look at the periodic table, iodine right here has got at least 53 protons and 53 electrons, which is way bigger than something like nitrogen that has only 7. And so, since it has a bigger molecular weight and more electrons, we'd say that CH3I has the much greater LDFs. Because it has more electrons that can do that momentary polarization and therefore stick together the best. The next question, the boiling points of CH3 and CHI are known to be BLOP and BLOP respectively. What substance has the greater overall attractive forces? So now we're looking at both of these in combination. We said that the CH3I has way better LDFs. It wins with LDFs. We said that CH3CN wins with the best dipole-dipole attraction. But then we take a look at the boiling points. And the boiling point for CH3CN is about 350. And then this one right here, CH3I, is about 315. By looking at the boiling points, we can tell how much energy it takes to put into these molecules to split up those intermolecular forces. And the more energy you have to put in, the stronger you believe those intermolecular forces would be. Since this one is about 40 degrees higher, we'd say that the CH3CN probably has the stronger intermolecular forces because it's harder to break up. And there you see an example of where dipole-dipole attractions actually overshadow the London dispersion force attractions. Even though this one has greater LDFs, this one still has LDFs too, this one right here doesn't hold together as well because it doesn't have as strong a dipole-dipole attraction as this one does. Dipole-dipole wins in this case, having a stronger attraction than this guy. Okay, let's look at a sample exercise 11.2. In which of the following substances is hydrogen bonding likely to play an important role in determining the physical properties? Methane, draw the Lewis dot structure here, CH4. Do we have a hydrogen bonded? Well, let's look at this. Hydrogen bonding, they say. What has to be happening for hydrogen bonding? Well, you have to have a hydrogen connected to an F, an O, or an N. Remember, I told you could remember as phone or as NOF, whichever one you want. Is there a hydrogen connected to an F, O, or N? No. Okay, so cross that one off. For sure, it's not going to be a methane. Next one, hydrazine. Ooh, hydrazine. H, N, H, and then we've got, I think it's a triple bond here. No, a double bond, I'm sorry. A double bond to another N, and then we've got an H and an H. Do we have a hydrogen connected to an F, an O, or an N? Yes, we do. So then there's a good possibility that this one's going to have hydrogen bonding with another hydrazine molecule to intermolecular force with. And then the last one, methyl fluoride. Methyl fluoride is going to look like this critter, CHHH, and then we've got a fluorine stuck off of here if you draw the Lewis dot structure. Do we have a hydrogen connected to an F, O, or M? Well, we got a hydrogen and a fluorine, but they're not connected together. So no, it probably have dipole-dipole forces because we're going to have an attraction for an electron here, from carbon towards the fluorine. But it's not a hydrogen connected to an F or N. And remember, to have hydrogen bonding, the H has to be connected to one of these. Okay, and then lastly, hydrogen sulfide. Hydrogen sulfide, of course, would look like sulfur, and then we've got a hydrogen here and a hydrogen here. Do we have an H connected to an F or N? No, so it's not going to be. So probably hydrazine is our best answer here, or our only answer, the one that will be affected by hydrogen bonding. Hydrogen bonding, remember, is probably the strongest of the intermolecular forces, and the reason that happens, the reason that it's so strong is because this F or M, highly electronegative atoms F or M, can yank the electron away from hydrogen, exposing that nucleus. Remember, the nucleus is just composed of one positive proton, allowing that to go out and do lots of attracting. Last question, sample exercise 11.3. List the substances Bacol, H2CO, HF, and Ne in order of increasing boiling points. Okay? Let's take a look and remember back to the very beginning of this video cast now and differentiate between these substances, because remember, things that are all molecular have only nonmetals in them. Things that are molecular have only nonmetals in them, and those are governed by the forces that we've been talking about a little bit ago here, were London dispersion forces, dipole-dipole forces, hydrogen bonding. Things that have metals in them, of course, are ionically bonded. Those are super duper strong. Remember, those particles are attracted by electrostatic forces, which are a lot stronger than the London dispersion or dipole-dipole or hydrogen bonding. And then we can look for other things that, it might just be atoms. It might just be atoms that are stuck together. So let's go through and let's organize each one of these according to what they are. Bacol right here, if you forgot, barium is a metal. Yes, yes, yes. Look on your periodic table. There's barium in the lower left-hand corner. See the full periodic table? Can you see it? Can you see it? Yeah, there's the barium down here in the lower left-hand corner. That's a metal. So this guy is going to be held together with ionic bonds. Okay, and it says increasing boiling point. To boil this thing, we're going to have to bust up that ionic bond between the barium and the chlorine, separate them. That's going to take lots of energy. So definitely our highest boiling point, I'm going to put it way over here, is going to be the BaCl2. You probably can't even see it. I put it so far over in the corner. That's going to be our biggest boiling point. So that's our biggest, and we're going to work our way backwards. Okay, now we've got hydrogen, CO, HF, and Ne. Of these, Ne is kind of a unique one because it's only atoms. And Ne happens to be a nonmetal, and neon's going to be held together only by this instantaneous polarization of these electrons. We could call it London dispersion forces if we want to, even though it's not technically an intermolecular force. It's like an interatom force between these two. And since neon doesn't have a ton of electrons, it's going to be fairly weak. It's going to be fairly weak, okay? But it is going to hold together. You know, it does have more electrons than, say, for example, something like hydrogen. Hydrogen, remember, is only HH like this, and it only has 2 electrons total. And this is a molecule, totally nonpolar, and the only thing holding it together is that instantaneous polarization right there, which with only 2 electrons is not going to be nearly as much possible as neon with something like 10 electrons. If you look on the periodic table, neon has an atomic number of 10. Hydrogen, way over here, has an atomic number of 1. So I would say that hydrogen is probably going to be our weakest held together, and then probably neon, and then we have to differentiate between 2 more here. These two, CO and HF, both are going to be polar molecules. I'm going to write on a different piece of paper here so I have a little bit more room. Carbon monoxide, looking like this, sticking together with another carbon monoxide, okay? That's going to have that intermolecular force due to its dipole moment. And then HF. And HF, I think we used an example just a little bit ago where we have a hydrogen connected to a fluorine, chlorine, or iodine, and so this is going to be held together by hydrogen bonding. Hydrogen bonds right here. And CO to CO, this is going to be held together by dipole forces. Dipole forces, of course, are ones where you have a polar molecule, but in this case it's not F or N. So what's stronger, dipole forces or hydrogen bonds? Now I should say this before we make that judgment. Are there London dispersion forces going on between the molecules here and the molecules here? The answer to that is yes. London dispersion forces occur in anything. But remember, they're weak compared to hydrogen bonding, and as we saw in our example before, they're fairly weak compared to dipole forces as well. So the governing force here, unless the molecule is way different in size, is going to be the dipole here and the hydrogen bonding here. Not that London dispersion forces aren't occurring, but they're just not nearly as much of a factor. So hydrogen bonding, of course, is much stronger than just a dipole force. So on a rating scale, we'd have to put HF as being the second best held together, and in the middle we'd have to put CO. So just giving the answer again, hydrogen is our weakest, so they would have the lowest boiling point, neon second, carbon monoxide third, HF fourth, and BaCl, of course, holds together the best of all of them because it is ionically bonded. This ends the first sample calculations video cast. When you come back next, we'll go on to the next page where we talk about determining some enthalpies, some energy when these changes of state occur, and we'll look at sample exercise 11.4.